Hey everybody, and welcome to the second half of Unit 1, and we are going to begin that with Lesson 4.1, where we are going to talk more about exponential functions, writing them, graphing them, analyzing them, and start solving some exponential equations. Now, to start, we are going to talk about Margaret and her winning the lottery, and she's going to invest her first payment of $50,000 over a 20-year period into an account that pays 5% interest, which I would love to find whatever account that is, because it seems a little unrealistic. Usually it's a lot smaller than that, but good for Margaret, paying 5% interest, right? Compounded annually. So going back to what we've talked about a little bit previously, we've talked a little bit with the money about that 1 plus r to the t power for annual interest rate. Same idea here, where we're going to basically each time be moving up a consistent amount with a common ratio. Notice we have a change of 2,500 here, but that's not the same here. What it is each time, though, is 1.05, right? 100 plus that 5%. So if we finish out the chart here, years since 2004, we have 3, 4, 5, 10 years. Make those jumps, and then we also want to start filling out the rest of this chart as well by calculating what each one is. So if we finish, filling out those final values by year 10, fill in the other ones as well. 81,444.73. Okay. So again, kind of talking about what we notice patterns in the table. We're increasing 1.05 times the previous balance. Okay. Now, what this again relates back to from the previous activities, the idea of our exponential functions, where we have this lovely format here: a times b to the x power. A is non-zero, b is a positive constant, it's not going to just equal 1, okay? And basically each time we can see that this is that previous times amount. It's increasing over time in this case, and we can kind of, we can double check that these values are okay, for instance, by looking for the common ratio to see the constant multiplier, right? Year 2 divided by year 1, we get 1.05, as well as if we take year 3 divided by year 2, we get that 1.05. So we can double check that this is honestly working itself out over the years. Okay. As we move on to the next page, we want to also show that as time goes on, that this is going to continue for another example. You can test that out on your own. But really what we're trying to do is, going back to Margaret's problem, is look at a function that is talking about this rule. And essentially, we're taking that starting balance of $50,000 and multiplying it each time 1 plus 0.05 or 1.005 to the t power. And then we could just plug in the year we are looking for to figure out what the balance in her account is. Now from here, if we start graphing, okay, and looking at what's going on in Margaret's account over time. A couple things. What we'll see here is this slight curve. Now, we're also going to want to use our calculators a lot today, so something that'll be handy for you to just have set is your table values. So, for instance, we can type in that equation we just talked about into the x power, and then we're going to go into our window, and we are going to set our window so that our x values are going from 0 to 15 years, like the book has, and going up by 1, year to 10. And then notice our y scale, we're starting at year 0, we're going up to 120,000, but we're going up by 10,000 each time, so we can set the proper upper window to get this on our calculators as well. So notice these guys are matching. And it'll help you kind of plot some in. Now, after we have this sketch, right? If we look here, after 10 years, part A is asking us what's going on in Margaret's account after 10 years. So a couple ways we can look at this. One, we can kind of use year 10 on the graph and approximate. It's somewhere a little above 80,000, maybe 81, 82,000. A way we could use this. So just kind of approximating on the graph. So right here, let's say at about 81,000-ish based on the graph. And the time it would need her to take to double her investment of 50,000, well, to get to 100,000, looks like it's taking a little over approximately 14 years or so, a little more than that, probably, right? Between 14 and 15, so 14.1, something like that. Okay, well, we have the equation, right? And we have either the ability to solve by hand or graphing calculators to test this out. So a couple things we can do here, since we do have the equation here on this graph. One thing we can do is, if we want the exact value for year 10 besides plugging it in, if we hit second calc, we calculate a value at year 10. So we can confirm that $81,000 piece here for part A. Again, we can even be a little bit more specific, that it would be $81,444.73. And then the time it's going to take to double her money, two ways we could look at that. We can graph when this is going to hit 100,000, and we could look for the intersection. Okay, so second, again, calculate the intersect here of our two. So keeps going a little bit here. Takes a moment. Scroll over. We set our guesses kind of right here. Enter, enter, enter. We see about that 14.2 years to get that. Or if we're solving this by hand, we're looking for this to equal 100,000. When we start solving, first things first, we want to divide by the 50,000 to get rid of that. So we end up with 2 when we divide by the 50,000. And it's been a while since you've probably talked about logarithms, but to undo these exponentials, we would want to take the common log here of both sides, and a property that you may or may not remember is that this is going to move out front then. So we have log of 2 equals t times log of 1.05. Divide both sides by the log of 1.05. And what you're going to notice is that our t, our time, again, log of 2, log of 1.05. This is that 14.2. Okay, so either way you chose to look at that, we can see the exact values. Okay. Now on the next page, I'm going to have you try this. Then again, we have this general format. This time, we're going to talk about Margaret investing only $30,000. Let's say she wants to spend some of it up front as opposed to depositing all of it. And what I want you guys to do is for 9 and 10, basically parts A and B here, essentially very similar to what we did here. You want to set up and solve, either by using the intersect on a calculator or logarithms, how long it's going to take Margaret to double her money yet again. So you're basically completing 9 and 10 right now. Now, something you hopefully acknowledged here, that it would still take approximately 15 years, again, approximately that 14.2, 15 if you're rounding up years to double, right? Just as it was before. And it's no coincidence that no matter what value we choose as our principal starting amount, what we're going to see here is it's going to take that 14.2 years. And the reason is, if we are trying to double our principal amount, right, and this is our constant setup here, when we start solving, dividing by that principal amount is going to give us this same setup each time, and that's going to cause that same thing. So doubling time will consistently be the same for the 5% years. Now, if we were to change the percentage, if the rate changed to something else, the doubling time would take a different amount of time. Okay? Now, this next piece then is basically asking us to take our three values. So we have A of t is that initial equation that we were talking about, the 50,000 times 1.05 to the t. We have B of t, which is the $25,000 amount. So it's same process, but different principal value. And then last but not least, C of t, where it's 50,000. Excuse me, 10,000. And if we graph each of these three values, okay, something we're going to notice about them, so again, kind of changing, you might want to change up your window a little bit to fit a little bit higher here. But as we graph these three and we look at the table here, notice the y-intercept is always your starting value, okay? And these are constantly increasing without bound, right? The graphs, they're getting steeper. It looks kind of slow, but they're continuing without bound. And for 17 and 18, then what we're noticing is if we have these exponential graphs, to figure out our rate, we're going to need to now take the amounts, and to come up with our rate, just as we did with the geometric sequences, we're going to divide those two consecutive terms, and we're going to find that we get 1.08 as that common rate of change, aka the rate is 8% based on that information from the graph, which means if we want to find the principal from this, then we can take year 2, very similar to our geometric sequence setup, year 1, the principal, because we have year 1's value, is what we're looking for, 1.08, and again, this is year 1's value, so to the first power, and that means if we solve for p, it's going to be 3240 divided by that 1.08, which is approximately here $3,000. Okay. All right, let's see. Last but not least for today, talk a little bit about the difference between that exponential function and if we take the exponential function raised to the negative x power. So if we take our calculators, let's just choose an a and a b value to be safe here. I'm going to choose just a to be 10, b to be 2. So we have 10 times 2 to the x, and then we're also going to look at 10 times 2 to the negative x. These parentheses there. And then I'm just going to zoom 6 to get this back into standard view, so we don't have our crazy big scale anymore. And as we look here, what's kind of the difference between these two graphs? Well, as we start looking, here they are. Which ones are increasing from negative infinity to positive infinity? Well, our a times b to the x graph is the first one. So actually what I'm going to do is I'm going to since these graphs are different color down here, switch that. And according to this, again, the one that's increasing is f of x. The one that was decreasing as we went from left to right, aka negative infinity and positive infinity, was g of x. Okay. Which of these has their x-intercept at a comma 0? Well, neither of them, because neither of them touch the x-axis. But which one of them have their y-intercept at 0 comma a? Well, both of them touch that y-intercept at 0 comma 10. So neither of them have that x-intercept since neither touch it, but both of them touch the y-intercept. Both of them also are going to have that horizontal asymptote at y equals 0. Okay, and we also are going to see that both of them are going to allow for all real numbers to be plugged in them. So the domain's all real numbers. Now here, both of them are going to have a range above y equals 0. Okay, but neither of them have the range. Nothing's becoming y value-wise below there. So again, it's another both, neither situation. Okay, and how are these two related to each other? Well, you can look at them as a reflection over the x-axis, excuse me, over the y-axis, aka we know that that's saying basically f of x is going to equal g of negative x. Okay, so that's how we write it algebraically, but looking at that, see it there. Okay, we'll talk more about why looking at that relationship is important in our next lesson. All right, thanks everyone.